Okay, so in this video, I'll try to explain you how you can use filter design and analysis tool of Matlab to design digital filters uh, in Matlab. So to get started, how you can access this FDAtool is you just type filter design analysis FDAtool in your main command window, hit enter, and it will turn you a graphical user interface for the filter design analysis tool. That's how it looks. This is your filter designer in Matlab, and by default it will show you a low pass response. Okay, so over here you're looking at one pass band and one stop band. So it's a low pass filter which is going to pass the frequencies around DC or low frequencies, and then it's going to stop the frequency. So what the legend says is that up until the Nyquist frequency, this is your frequency legend, frequency axis, and on the vertical scale you have the magnitude in dBs. Okay, so it could be the pass band tolerance, which is specified by a pass, could be 0.1 dB if it is very stringent requirements, or 1 decibel, whatever you choose. So you can set your this vertical scale tolerances. A pass is the pass band tolerance, and then in a stop band, this is a stop. So you can set those tolerances in this in these settings over here for the magnitude specifications. For the frequency scale, you can set the specifications according to your sampling frequency under the frequency specifications tab. So what you do is, so let's take a simple example. I mean, you might want to design the other type of response. So if you want a high pass, you select a high pass like this, or from the response type. So you see the stop band and the pass bands are inverted. Okay, so you're going to reject the low frequencies and you're going to favor the high frequencies. For example, if you have a band pass, then there could be one pass band. So you will pass the frequencies between f pass 1 and f pass 2, and you're going to stop the undesired frequencies between up until f stop 1, and then higher than f stop 2 up until the Nyquist frequency. That's the half of the sampling frequency. Similarly, you can have band stop. So this is the um, so that's how the magnitude response or the frequency response for band stop will look like once you design the filter. So the pass band tolerance will be between a pass 1 and a pass 2 in the pass bands, and for the stop band this will be a stop uh, between f stop 1 and f stop 2. Okay, so let's go ahead and design a low pass response. For example, let's say I have a signal which has frequency components, or probably I should just write I should construct a hypothetical signal. Let's say a sampling frequency of 1000. Okay, and suppose I have two tones, two tone signals. Let's say f1 is 200, and then another tone occurs at 400, let's say. Okay, and if I need to construct a time domain signal out of this, so I need to define a time vector. So let's go ahead and do that. So let me choose the step size as 1 by fs, and okay, let's create about 10,000 samples. So this is 10 minus 1 minus 1 by fs. So you see, I have a time vector in this workspace, which is an array of numbers. Okay, 1 into 10,000. Double is the data type. So these are the array. It's a time array vector. Okay, having step size of 1 by fs. So let's go ahead and create some signals. Let's say I have a tone signals which consisting of f1 and f2. So let's create this tone out of cosine or sine functions. You can set any amplitude. So let's say 100. It's not important whatever the amplitude you have over here. The important thing is let's try to construct a frequency signal, single frequency signal over here. So I have signal x1. Then let me go ahead and construct another signal x2. So this is my x2. So whatever the amplitude is, let's make it 500. So 5 times the amplitude, and the frequency is f2 over here. Okay. So I have these two signals. So let me have another third signal, x1 plus x2, which is the linear combination of these two signals, x1 and x2. And the job is, your job is to retain, if we are going to have a low pass filter, so let's retain the first component, 200 hertz, and reject the higher component that is at 400 hertz. And for that you can have a sampling frequency which is at least twice the maximum. I mean, minimum will be 800, so 1000 is good enough. So sampling frequency to avoid any errors in reconstruction or in sampling. um, so let's see how this mm, how this tone signal sounds like. Okay, so if I play this sound, the tone signal x1 on my sound card, you will hear something like, it's a tone, it's a tone. Okay, let's hear this again. Low frequency tone. How about high frequency? Let's change it to x2. So now you're going to hear 400 hertz. Okay, so the pitch is more. Okay, so that's expected. So what if we make a linear combination and then you play it, then it will hear, you will hear the sound like this, right? So the idea is to filter out x2, okay, which consists of the 400 hertz tones. Filter out x2 from x, which consists of both x1 and x2, and you're left with x1 again, and the output should sound like x1. How to do that? And by the way, if you want to visualize this, the time domain plots, you see, can you plot this? Oh, hang on. We can plot this like this as arrays: t, x1, then t, x2. So with time, we have these two plots. You see, one of those magnitude was 500, and then the other is 100. So this 500 is just covering up this 100 one. So let's see if we can find this 100 tone signal buried somewhere over here. Okay, you can see this is coming up. So these blue ones are my 100 hertz tone signals. Okay, let me pull some. All right, some sinusoids. For example, over here, if I put some markers, I might need to zoom out a bit, and then if I put a marker, create new data type. You see the difference between these two peaks. It should be about 100. Sorry, 200. Okay, so this F1. This F1 is what this F1 is corresponds to the blue signal. Okay, so if we have over here, then another one would come about here. Okay, so the difference is about you see the difference between not in the y but in the x. So 1.189 minus 1.184. Let's calculate 1.189, 1.184, about 0.05. So 1 by answer is about 200. This is my F1. Okay, this is my F1, which I see over here is buried beneath this 500 high pitch sound, high pitch tone signal. Okay, so if I'm going to zoom this out, I can see those 100 hertz, 100 amplitude, 200 hertz tone. Okay, all right. Now let's get back to the problem. The problem is to use this FDAtool. So once I have this FDAtool window open with me, I can select the low pass filter response to retain F1 and to reject F2. What I'm going to do is, well, there are options for the design methods. It's up to you. You can use infinite impulse response digital filter or FIR digital filter. Well, as a filter designer, they have their own choices to select any of those two. If you're looking for stability, unconditional stability, the FIR filter is by default is the choice because the poles are at the origin, so you don't need to worry about the stability. However, the number of coefficients and maybe the VLSI implementation cost of FIR could be higher than IIR. So it's a trade-off, okay? And then even in FIR, there are least squared methods, window method, okay, constraint least squares, complex equiripple, maximally flat, least pth norm. So you can select any of those methods. So let's keep it this simple. Let's consider an equiripple filter design. And what I'm going to do is I'm going to select let's say a stiff tolerance of zero point 0.2 decibels, which is the pass band. So in the pass band, my requirement is that the frequencies are within 0.2 dBs. Okay, and then in the stop band, the attenuation should be at least, let's say, 60 decibels. Okay, so I'm going to loosen this up. At least 60 decibels of attenuation in the stop band, that is below zero, so it's minus 60 decibels. My sampling frequency for the frequencies is 48K is very high, so let's keep it at 1000. And my F pass is I'm going to pass up until, so I need to retain, remember I need to retain 200. Okay, so I need to retain this frequency component 200. Okay, and I need to reject this 400 component from the signal X. So I can select this pass to this can be selected as 300. Then f stop can be selected as let's say 350. So it's a very sharp roll off for this frequency. So at f stop starting at 350, I should have an attenuation of 60 decibels. Okay, so the frequency response should drop to 60 decibels. Either you can specify the order in the filter order. I need, for example, 30th order or 100 order, whatever. But by default, if you keep it minimum order, the FDAtool is going to design the filter with minimum number of poles and zeros that will satisfy the given specification. And the specifications are your pass band, stop band, attenuations, and the frequency scale axis that you are specifying. Okay, and the density factor is all right. Let's not touch this as well. If you're going to increase this, it is going to increase the computation cost. Okay, you will have a more finer, let's say, the frequency grid. Okay, so let's keep this as it is. And so these are our specifications. Let's go ahead and design the filters. Here you can design the filter just by clicking this option. So let's see what we get. Okay, here's the magnitude response in decibels. If you right click on the vertical axis, you select magnitude, you can see those equiripples because we selected the equiripple design. So in the pass band we have the maximas reaching the equal amplitude, minimas reaching equal. So these are equiripples in the pass bands. Then in the stop band we had at least minus 60 decibels of attenuation starting at 350, and we were interested in having frequencies up until 200, and we were supposed to reject 400. Okay, so 400 is not desired. So over here, if you see this menu, you have if you hover your cursor over here, it shows you magnitude response, your phase response. So if I'm going to go ahead and click the phase response, I have a linear phase. Okay, we have a linear phase. This is the phase in radians. Okay, versus frequency. You see, the frequency response is complex. Generally, it's complex. So it has a magnitude part and a phase part. So this is showing both the magnitude and phase. So another advantage of designing a digital filter, which is a finite impulse response (FIR), is that you have a linear phase response. By linear phase response means the group delay is constant. So this is your group delay. Group delay is the gradient, or this is d phi by d omega. Okay. So if you click on this, of course you are going to get a constant response with frequency, which means that if the frequencies are starting together, they don't arrive together, there's a phase distortion. So in music signal processing, for example, if you have an MP3 file or a WAV file and you're going to reject some frequencies, you're going to use a Matlab and you're going to filter out that WAV file or a music file or a speech signal, whatever it is. If the phase is not, if you don't have a linear phase, there's a phase distortion, okay, and that's not desirable. So in the menu, you can go ahead and you can check out for the impulse response. So these are the samples. We have finite impulse response. This is your impulse response or your finite number of samples for FIR, and they are symmetric in nature. Okay, so for example, these two are the same, these two are the same, so they're this for basically for a symmetric impulse response you have linear phase response. Okay, so if the coefficients are symmetric, you have a linear phase response, and this is only achievable in FIR, not in IIR. Okay, if you look at the pole zero response, you see all the poles for FIR are at origin, uh, which results in inherent stability. Then you have minimum and maximum phase zeros. Zeros can lie anywhere, okay, with respect to the unit circle on the z plane. All right, but in IAR, if any pole is outside the unit circle, you have an unstable digital system. Okay, so you don't need that. So this B and A, they represents these filter coefficient that we are interested. Okay, so what we're going to do is we are going to export these filter coefficients from FDAtool into our workspace. Okay, and we are going to use this in our workspace to filter out the signal X, leaving behind X1 and filtering out X2, okay, which was F2. So let's see how we can do that. So this is the information regarding the filter we have constructed. The length is 51, so the order is 50, all right, because we selected the minimum order, so that is the minimum order satisfying the given specifications that we have given in terms of frequency and the amplitude specs. The filter is stable, yes, and this is type 1 linear phase response. For in terms of VLSI, the number of multipliers, adders, the number of states requirements are as given. Okay, so this is if you are employing a direct form FIR structure, these are the requirements for a number of multipliers and adders. But this is not important if you are going to use these coefficients in Matlab to filter them out. For VLSI, yes. Okay, so you go to File and you hit this export. All right, select export, choose whatever these coefficient is. So I'm going to use this. Let's keep this as B or whatever you want to assign. So this is going to export to the workspace coefficients, and then click on export, and it will create a variable B which is of the same length, which is the filter length. So let's see what we have over here. You see B is my vector 1 cross 51, which consists of filter coefficients. Okay, so in my variable B, let's see if we can, yeah, so minus 0.0035 minus 0.0042, these are my filter coefficients, and these are symmetric. So the first one will be the same as the last one, minus 0.035. Okay, then minus 0.0042, then 0.0042. So this is a symmetric coefficients that are yielded or produced in FDAtool. Now I have this exported them, and because of this symmetry, we have a linear phase response, remember. So what I'm going to do is I'm going to use these filter coefficients in my workspace, which I have in my workspace in command window to filter out the signal X, okay, the signal X2. So okay, let's close this. Then by the way, if you're interested in looking at the frequency response of the signal, you can use the frequency Z command, frequency Z, which is the frequency response through Z transforms. I mean, if you're going to evaluate the Z transform on the unit circle, because Z transform is a generalization of discrete time Fourier transforms, and if the Fourier transform exists, the region of convergence must include the unit circle. So if you're going to evaluate these through Z transforms, if you're going to look at the frequency response, you can use frequency Z in Matlab. This is the built-in command. So let's have a look at X, and let's evaluate this as, let's say, 512 points, or I don't know, 1024, depending on the resolution you wish to use. So this was my X signal. Okay, so let's see what it returns. So we have a normalized frequency scale over here, and this normalized frequency scale is I'll tell you, this is like 2 pi multiplied by f over fs. So for example, over here we have okay, so let me write this normalized frequency. Omega 1 is 2 by f1 divided by fs. So let's see, this is 1.2566, okay, and what is omega 1 by pi? So that's my 0.4. So I have a peak at 0.4 over here. If you're noticing it over here, around 0.4, okay. There is a peak at 0.4. So there is a frequency component at 0.4. Then there's another frequency component which is twice of that. That is 0.8, okay. So this, because this is normalized and this is multiplied by pi radians per sample. Okay, so I've normalized this by pi over here. So I have actually two tonal signals, 0.4 and 0.8. So this is my original signal, which is unfiltered as of yet, which we are going to filter. So we're going to retain 0.4 component. We're going to reject 0.8 using low pass filter. So there is a command which uses, well, if you are designing this filter in the command window using other commands, if you're not using this FDAtool, filter BAX is the syntax. Okay, so if I make this a new signal Y, so filter BAX is my signal. Well, B and A are exactly the poles and zeros which we have looked before in the filter design analysis, and these BAs are my filter coefficients. They refer to the filter coefficients. Okay, in FIR case, A is always set to 1, right? I have B, which are my filter coefficients. Okay, so I'm going to set this A equal to 1, then I have B, and this X is my signal which is to be filtered out, right? In other words, this is also the convolution of the signal X with the filter coefficients B. Okay, so let's use this to create a new sequence Y, which is of the um, same length as X, and if you are going to plot Y with respect to T, you will see that I don't have the two tones right now. Okay, if you recall, the signal we constructed, we had 100 cosine 2 pi f1t and then 500 cosine 2 pi ft. So I don't have any component of 500 anymore, right? It's 100, and there's only one tone, so you can zoom it up, you can zoom it in, and you for yourself you can see that I just have one frequency component that is being retained after filtering. And if you're going to if you're going to have a look in the frequency domain after filtering, it looks like this Y, and let's say the same number of frequency points. So I just have this at 0.4. If you recall, we had another tone at 0.8 which is gone, which is attenuated. Okay, so 0.4 is what I'm left with only. So let's listen to this signal Y, okay, which is exactly one tone signal. Okay, so, and this tone consists of only 200 hertz. So sound on my sound card of the sequence Y is like this. Okay, which is very similar to what I have in X1. This is a low pitch sound, and my high pitch sound X2, which was another frequency component which was occurring on the normalized frequency scale at 0.8, is gone. Okay, look, this is gone, right? So if I'm going to hear X, which is combination of both of these, X1 and X2, linear combination of X1 X2, right? Now Y is like this. So this is basically which is same as X1. All right. So if I'm going to plot T X1 T Y, you see, the thing is we don't have much of a difference over here. It's the same overlapping signal after filtering. It's about the same. Yeah, so I think the filter has done a very good job. So this was just an example to show how you can use the filter design analysis tool of Matlab. Okay, it's a powerful graphical user interface which comes with those specifications. You select the response type. Okay, if you're very well versed in digital filter design, you can select according to your own needs the design method. For example, if you're going to use window, it's going to ask you instead of density factor which window you are interested in. Kaiser window, Hanning, Hamming, Gaussian. Okay, so window design has its own perks. You avoid the rectangular window, which might result in Gibbs phenomena. Kaiser is a better choice than that. Okay, similarly, you have the other constraint least squares, which are numerical methods of calculation of these window methods. So the options are changing. Okay, for example, in least squares, okay, you're different. You have W pass and W. You are entering the weight values for each pass band and stop band, and you have maximally flat options. Okay, so if you can as on your uh, it's your prerogative as a filter designer which method you're going to use. If you're going to use IAR, then if you remember in your DSP courses, is the infinite impulse response filter design is primarily it's based on the analog filter design. So you are looking at Butterworth, Chebyshev, elliptic filters. These are analog filters, and then from bilinear transformations or other S to Z transformations, you transform this to digital filters. Okay, so primarily you are designing in the first place an analog filter if you're going to design an IR filter, and then you are going to transform it. So you don't have to do anything. I mean, if you're going to select an elliptic filter, just give the specifications. Okay, design the filter, bring the coefficients in the workspace. Okay, from file, export, and you will have a similar performance. Okay, you don't have to do any transformation. The FDAtool is going to do this for you. Okay, you just need these filter coefficients in your workspace. Okay, use them to filter out the signal. You can use music files, MP3 files. Once you have those coefficients, well, you are good to go. Whatever frequency components you want to filter out, just just give those frequency components and specifications over here. Okay, just give according to this pass band, stop band, whatever the response is, and just filter out the signal. Okay, so that's about the filter design analysis tool, right? Thank you.